All right. Hi, I'm Dave Hunter, Senior Principal RF System Engineer at Vanteon, and we're going to talk about basic receiver design. So here we have a block diagram of a typical super heterodyne receiver, which, by the way, came out in 1919. So 100th anniversary of the super heterodyne this year. So we start the basics. We have an antenna, and we have an input bandpass filter, a low noise amplifier, mixer, local oscillator, IF filter, which is also bandpass, an IF amplifier, detector, and in this example we're going to talk about audio output. So the RF signal's on the amplifier, and you want to limit the amount of RF signal you have coming in. So that's limited by the bandpass filter. So this is your overall band for your frequency. So for example, take your FM radio, it's 88 to 108 megahertz. That would be your band of interest, and so your bandpass filter would block out signals outside of that and keep the signals that you have. So the low noise amplifier, what this does is this sets the sensitivity level or noise figure. So we'll talk about in RF they talk about noise figure all the time. And the way the low noise amplifier works is it boosts the signal and limits the amount of noise that follows. So you want a low noise figure as possible, and it depends on your application. For the FM band, it doesn't need to be real big, but typically you'll find noise figures of, for real sensitive things, of 0.5 dB to 10 dB. And most of our receivers that we do here is around 2 to 3 is our goal for noise figure. So what that means is only 2 dB more of noise is added to the noise that came in. So from the LNA, this adds gain and limits your noise. And then that drives the mixer. And the mixer is fed by the LO. What a mixer does is it gives you the frequency out is frequency of the RF plus the LO, or the frequency of the RF minus the LO. And the way a mixer works, it's basically a multiplier. And so you get both sets of frequencies out, which are known as intermediate frequencies. And so typically, based on how you do your system design and how much tuning range you have, you pick your IF frequency. Based on the parameters of what your LO tuning can be, what your input comes to be. Usually, it's the subtraction most of the time in most of your applications. So, and then you pick an IF that is appropriate, and the idea behind the intermediate frequency is you have this wide range of frequencies, and you want to put all your gain at one frequency rather than have it spread apart. So that's what the key of this does, is it brings this set of frequencies down to a single frequency. In a typical FM radio, you have your IF is 10.7 megahertz. So your LO is going to be 10.7 megahertz above your RF frequency to give you the subtraction to 10.7 megahertz. And now you have an IF bandpass filter, and this is bandwidth is based on how wide the signal is you're looking for. So if you have a very wide signal, you want a wide IF. If you have a very narrow signal, you want a very narrow IF to limit the other noise in the system. And then you boost that mixed signal with the IF amplifier for a lot of gain. And then after that, you have your detector. And so typically for IF amplifiers, you may have gains of 30 to 50 megahertz, 50 dB, where your LNA may be only 10 to 20 dB. And that has to do with, some of it has to do with how amplifiers are designed. And if you want low noise, you don't get a lot of gain, and vice versa. And so you'll put a little bit of gain up front, and that'll set the noise figure for the whole system. And then you put all your gain here in your IF amplifier, and then that goes to the detector. And so the detector could be, in this example, it's an FM demodulator, but it could be AM, could be data, digital, whatever you're looking for. So those kind of the basics of a receiver. Thank you.